Hi students, today we will talk about normal distribution and its applications. Any variable that follows normal distribution with two parameters, mean and variance or standard deviation. This is how the norm we write it down. X follows normal distribution with mean mu and variance sigma square. Mean we call the location parameter, whereas standard deviation we call the scale parameter of normal distribution. Why is this so? When we draw the curve of normal distribution, it is looking like a bell-shaped curve. Bell-shaped curve is a symmetric curve. Therefore, we have a consensus that whenever the distribution is symmetric, then its mean and median lies at the same position. Whether its mode lies at the same position or not, it depends upon the fact whether the curve is taking highest position at the central value or not. So over here, curve A I have drawn is a symmetric curve that has a center at mu. Therefore, its mean, median and mode lies at the same position because curve is taking highest position at the same point as well. So mu helps us to identify the location of the center of the curve, therefore we call it location parameter. To understand the scale parameter, what I have done, I have drawn two curves, second curve as well, which is labeled as B, drawn in red color. You can take notice of one thing, that both the curves, what I have drawn as A and B, have the center at the same values. But as far as the degree of dispersions are concerned, curve A has a greater degree of dispersion as compared to curve B. Therefore, we can say that standard deviation of curve A is greater than that of B. Since standard deviation is the parameter that helps us to identify the degree of dispersion with respect to the mean value, therefore we call it scale parameter. Now the commonly used variables that follows normal distribution are height and weight. Height and weight values in a certain age group for the students or for individuals can be referred as an example for the normal distribution random variable or a random variable that follows normal distribution. Normal distribution has a continuous random variable. So height and weight are both the variables that are continuous in nature. And why we are referring these two variables, height and weight, as following a normal random variable? Because when we observe heights of individual, we can observe there are cases of extreme height values as well, along with moderate heights. But as far as representation is concerned, so we observe that there is a greater representation or maximum representation of all the individuals who have height closer to the mean values. But as we move away from the mean value, that is for the height greater than the mean value or the height less than the mean value, we observe the area under the curve decreases gradually and with a similar pace almost. Therefore, we can assume that variable height follows normal distribution. We can also assume that variable weight also follow normal distribution because we observe individual with extreme weight values, but the percentage representation of the weight values closer to the average or mean values is almost highest. And as we move away from the mean values, for the higher weight values to be located on the right part and for the lower weight values to be located on the left part, With respect to the mean line, we observe representation reduces gradually. And yes, we may have individuals with a very high values for the height and with a very low values of the height, but the representation in the entire data for those observations will be very limited. Therefore, we observe tail formation under the bell-shaped curve in the extreme areas. As far as PDF is concerned, so this f of x is representing the PDF of the normally distributed variable, and we write it down as 1 upon under root 2 pi sigma. Sigma is again the parameter for standard deviation. E to the power minus half this x minus mu divided by sigma whole square component. So the factor that is inside the whole square component we refer as z. Z equals x minus mu divided by sigma is the formula by using which we can transform our random variable x into random variable z. And you can see that if we take x equals mu, then the corresponding z value for x equals to mu is 0. This is how we can refer it. Over here I am making change. This is not 0. 0 I was referring the z value, but when we take x equals to mu, so this difference goes 0 divided by any number is equal to 0. So central value under the curve of z is 0 across x equals to mu. Similarly, for the same reason, all the values located below the center line, all values of 0 are negative, whereas all values located above the center line of z equals to 0 are positive for that reason. And transforming x, random variable x, to z is with a purpose so that we can use a table that gives us the probabilities across each value of z once we transform x is equal to x into z. So you can have a look on this table. It has 2 pages. This is the z table. The first page contains negative z values in each row. Let's take, if we would like to locate minus 2.45 as a z value and the probability corresponding to it. So we need to select or move across the row of minus 2.4, and it's the fifth column. So minus 2.54 would give us the probability of minus 2.45 would give us the probability of 0.0071. All the probabilities that are included in the negative z table are equal to or below 0.5, and then all the probabilities in the positive z table are exceeding 0.5, you can say. So positive z table we use in case when we are interested in the value and in the probabilities across z values above 0, and for any value of z below 0 we refer negative z table to get the probabilities located.